Okay, my friends, this is kind of crazy. I just did a video about the Iceland volcano. And I think I understand it. I thought I understood it well. However, when I went back to verify some of the things that I said in the clips, I noticed something that I hadn't seen before. And it changes, to a degree, my perspective on it. And I think I now understand it a lot more. I'm going to show you the clip. First of all, let me just explain what the new information is, and then we'll go through the first video that I did. I was just about to post it, and then I realized, wow, I missed this. So let's see, what did I miss? Okay, so what did I miss? I missed that right there. Originally, I was trying to understand where all of this was coming out. I believe it's all coming out right at that spot. Now, I also believe that it's probably downhill this direction. So most of the flow went this way. It was strong enough that it tried to go up this way, but you know, it's not pushing hard that way, and it's probably gravitationally flowing down this way and this way. Now, what happened here? What the hell is that? What's going on there? I'm going to tell you right now, I think that's the membrane of some gigantic creature, and it hit that membrane and it's doing its job. This is the fluid-filled highway. These are fluid tubes. These aren't just running off down hills and valleys, although they may be, because a lot of the valleys are actually tubes that were at one time arteries and veins and so forth. But it's running down through whatever this was before. It's flowing that direction. I don't think it's erupting here. You can see it bubbling like crazy all the way down here, but I don't think there's any real eruption here. I think it's just an enormous flow this way, and it is flowing like crazy. Amazing amount of lava is flowing. So this, I think, is a membrane. I think that's a membrane, and this, again, the flow would be down this direction. So whatever happened here, it killed it. Well, killed it, when I say killed it, it destroyed whatever tissues were in there. And those tissues are not eroded. I mean, they're not degraded yet totally. That's why these things are eroding, exploding so much, because now they're warming up, and the decomposition is creating spontaneous combustion. And if it's plugged up so hard that it can't get out, boom, you get an explosive eruption. This is not plugged up so much, it can just squirt right out of there. Now, what kind of a feature that was, I don't know. I want to know what the chemistry is of the lava flow here. What's in this chemistry? That can point to what the source was. But this right here, in my opinion right now, that's the source of this flow. And there's no other reason for this to happen in my mind, other than that this would be some form of a blockade, which is a membrane. And it's a fluid-filled membrane, so these fluids would flow down through there. And you see how it's smoking off in here? I'll bet you if they tested those gases, they're going to find out they're heavy in phosphorus, because that's what's in a phospholipid membranes. If it's burning a membrane, you're going to get a lot of phospholipids. Well, phosphorus. Well, actually, I found out that you got sulfur dioxide, carbon dioxide, and hydrogen sulfide. Well, what's hydrogen sulfide? S is sulfur. And you got sulfur dioxide, hydrogen sulfide. We got a lot of sulfur. Well, where's sulfur? Sulfur's right here. It's right above phosphorus. Phosphorus is the phospholipids. When you heat something or infuse a ton of extra energy into something, you can literally bump it up. It doesn't decay downwards like you're pulling stuff out. You're pushing in, so you push phosphorus up to sulfur. That's why we got so much sulfur here. So I'm not seeing the phosphorus, which I was thinking, well, it's going to boil off this phosphorus from the membranes. Well, the phosphorus, instead of being just vaporizing off, it's converting it into sulfur, oxygens and hydrogens attached to the sulfur. like it's burning it. I mean, the phosphorus, and it turns it into sulfur. And that happens, you can look, well, let me show you. Okay, here is the process. Normally, you're going to get smaller atoms. However, in certain situations, atoms can be involved in nuclear reactions that result in heavier elements being formed, going from phosphorus up to sulfur. It's common in nuclear fusion and nuclear capture processes. Well, what does that mean? That means extreme energetic reactions, extreme energy, which is in a volcano, that's pretty extreme. So we are going to get heavier atoms. That means we bump up from the phospholipids, which is the membranes, up to the sulfides and sulfur. All right, I'm just going to tell you right off the bat, something is going on in the digestive system of some gigantic creature. And one of these tubes is backed up and exploding. Now, what it backed up from? Was it in the it's probably in the digestive system, I would think, but I don't know. This is, you got all kinds of organs going on in here. There's secretions of all kinds of juices and this and that. These creatures in the Iceland and Greenland and all these places where they've been pretty well frozen for a very, very long time. Now they're starting to decompose. And when they do, they start to explode, literally. It's like spontaneous combustion because they were preserved like, you know, fleshy and body tissue and everything in these cold areas. And now they're thawing out and they're creating explosive gases and just combusting. But it's combusting all the way down one of these tubes. Now, and you got all kinds of tubes inside. I mean, you got all kinds of things going on here that could literally explode when they start to decompose. Now, hold on, let me put this up here. Now, somewhere in here this is happening. And when you see it flare out like all that, there's all kinds of body tissue that's very, very webby and filled with little blood vessels. And somehow that stuff that's coming down, it's going all into these little webbing. It looks to me like it's filling out a bunch of blood vessels. And I mean, you got a bazillion blood vessels. So wherever it's leaking into, I don't know. It could be in the spleen. This area here looks a lot. I mean, it's just everywhere in the body. There's a ton of stuff that could do this. And when I say can do this, this is what I mean. That, to me, is some kind of a tube. And it's been filled up with all that festering biology that's just rotting, basically, and combusting, and pushing its products down into here, into the webbing of whatever this tissue was. And it had to be some kind of a tissue. All right, because these things don't start from nothing. You see this? Look at that. To me, that is some kind of biology. It's coming down like a main artery type thing, and then branching out into the kidney, or I mean, I'm not sure what it is, but I'm sure it's an organ of some sort. And why this is festering right, it appears to be festering down this line here very, very strongly, and pushing its contents out into whatever little tubing is around here. And this is tubing stuff. This isn't just flowing out into, you know, big globs just hanging over. Some of it is, yes, but this is not. This is going through tubing. That's not just an accident that it shows up like that. It's coming out of here, and instead of just making a big glob out here, which that's what you expect, it's flowing out through a network of tubes. It's a network of tubes. In my opinion, I could be wrong, but I don't think so. Okay, the truth is, I'm not 100% sure of what I'm talking about here, but that's why I'm asking. Now, I think it must have, the source must be along this line right here. All right, is it going that way, or is it coming this way, or is this feeding both directions? I think it's the main source. It's got to be coming from somewhere. Although it's the whole tube is erupting at the same time. However, that tube has to go into something, and I think it goes down inside to somewhere that's feeding it, and it's just pushing that down, and it's running fast. I was amazed at how much magma is flowing. I mean, it's flowing fast. Now, I think it's flowing out of here, and then some of it's going this way, but it just doesn't have the. It's easier to go this way. So it diverts itself and comes down. Now, what is going on here? You see that line? That, to me, it looks like it could be like even a membrane, which protected this area over here, which looks like it could have been some kind of an organ, or I don't know what it is over here. But this intrigues me. That looks to me like it could have been a membrane. And why is this all blacked out over here and this is still cooking? And I don't know when this picture was taken. I found it on the web today. And it's cooking here. It's really good. And again, I don't know where, I believe it must be flowing from here down this way and really clogging up basically in this area and really getting pumped up and then squirting through here. And at this point, it gave up trying to go this way and found an easier path down here. That's all I can take out of that. And then this is all smoky, but you don't see the smoke anywhere else. Why is it smoky here? It's hitting something that it's cooking. It's cooking something right on that line. To me, that's the way I'm looking at that. So what would it be cooking if it's not cooking anywhere else? That's why I say I suspect a membrane here. I bet you if they tested the gases here, they'd find out they were phospholipid related gases, phosphorus. And they should be able to test the gas there. That would be interesting to see. That is some pretty serious bubbling. And it's going all the way down that tube. And it's really intense in this one section of the tube. So that's the source, in my opinion, and then it flows one way and the other way, it appears. You know, I'm looking at this like it might be a lung here, and that might even actually be another lung, but this one here is easily invaded, and that one is not, but it is getting some invasion. And you can see that there's a lot of action going on here. But this whole thing is feeding. Now, could it be feeding from the heart? Is the heart around here somewhere? Because blood is made of hydrocarbons, basically, which are the things that burn and bubble and boil and you know, blood is combustive when it gets to a certain temperature. All right, this is pretty much all you have to know about spontaneous combustion. It's a reaction, basically chemistry, and when heat accumulates without being able to escape, the temperature can rise enough to ignite the material. For example, when organic materials, like hay, straw, oily rags, body parts, bodies, when they decompose or oxidize, the process can generate enough heat to cause combustion. And it also causes a large amount of methane gases to be released. So you have pressure. The pressure causes the more heat. And the more heat, the more pressure. All of a sudden, it pops like a cork in certain places. In other places, it's just allowed to flow out. That's the case in this particular eruption in Iceland. So I think I've given a pretty good explanation of why this is giving off these sulfur and sulfide gases in this membrane area, probably everywhere, because everything is coated with a membrane. So wherever heat flows through there, it burns it off and changes the phosphorus up to sulfur. Okay, here's the whole process. Don't get freaked out. You don't have to be a chemist or a nuclear scientist or any of that stuff. This is very, very simple. It has just not been understood. You will understand it because it's so simple. Phosphorus is not like one big thing called phosphorus. Boom, that's it. It's just phosphorus. No. Phosphorus is just like every other atom here. And it's constructed of a whole hell of a lot of tiny ones. Sometimes you don't have enough of them, but it's still considered phosphorus, and it wants to add some. Sometimes you have too many of them, and they want to give them up, and it shoots them off. Now, what happens in that case? Well, it either decays downward, which you normally say decay goes downward. No, not always. It can go up. And not only can it go up from nuclear reactions, which fuse energy into it, it can go up from like volcanoes and all kinds of really intense radiation, because it's adding particles to bring it up. All right, when you burn something up and boil it and so forth, it takes them away. So the phosphorus, which is what we're talking about, is a membrane. And that's what's burning up there in Iceland. It can either go up to sulfur or it can go down to silicon in that area, and it's going both ways. And here's the process. All right, these are all considered phosphorus. All of these, every single one of these, but they're all different weights. This is the weight, 26, 27, 28, 29, 30, 31, 32, all the way up, like they have more and more and more particles. Down here, they decay. When they decay from phosphorus, they go down to aluminum or silicate or even down to magnesium. See it? Magnesium, silicon, aluminum. Now, once you hit stability, all right, now don't forget, you can be just as good as a nuclear scientist right now. Once you hit stability and you have all the particles you need to fulfill stability, which means I don't want to give any up and I don't want to take any down. I'm locked in and I'm stable because everybody knows where they're supposed to be and they're staying there. That's what stability means. When they don't know where they're supposed to be and there's not enough of them and they're all jumping around trying to find a place to be, that's unstable. And then you have what's called a half-life. It can only stay in that unstable mode for so long, and it will sooner or later keep adding particles until it gets up to stability. That's all half-lives are about. And this is how nanoseconds, milliseconds, minutes, how long they can stay in that condition without decaying. And decaying means either going down from stable or going up from stable to sulfur. That's what's coming out of the volcano, all these sulfur components, because they're coming up from phosphorus. It's such an intense reaction that the phosphorus is being pumped up to sulfur. That's exactly what it says. It can, under these kind of intense reactions, it can pump up. But not only that, enzymes can do this. Enzymes, they do chemistry that's just so elegant. They don't realize this. In the human body, that's what's working with all these half-lives, is the enzymes that are created by bacteria, and they go through the body and they click chemistry, and an enzyme doesn't even get used up. It comes up and it sees a phosphorus or something or the other thing, a carrot, and it needs phosphorus out of that carrot, and there's no phosphorus. So you can go, and all of a sudden you got phosphorus. That's what enzymes will do. But you have to have the enzymes. The only way you get the enzymes is to have the bacteria. The bacteria create a ribosome which holds that enzyme. When the enzyme's needed, it pops open and it does the chemistry to break that carrot down to make sulfur or whatever it needs. That's how click chemistry works. There's a lot of things that have been discovered because of mud fossils, a lot of things. All right, I just got to get deep for just a second. Don't get upset. It's not going to be hard. You're going to love this, especially if you got kids or anybody that's really interested in chemistry, physics. Now, all of these are phosphors, but they're all different weights. Now, the only thing that has weight is a dark particle. They get more and more energy, but they still have the same, the dark particles get more and more, so they're going to attract more and more white particles. That's the deal. Now, dipole electron flood theory explains this very well. Now, I'm going to show you what happened. I showed you that they're not just one big mass that says I'm a phosphorus. No. They're a whole batch of little particles until they get to a point where they say, all right, now I am a stable phosphorus. I weigh 30.97 atomic mass units. All right, and then it goes up 30, 31, 32, 33, 34. So it's just getting more and more and more particles. And the white ones don't have any weight whatsoever, so it has to be adding dark particles. Dark particles attract more particles. Let me show you what happens here. This is dipole electron flood theory. These are the only two particles that exist. The only two. These have the mass. These have no mass whatsoever. Zero, literally. It's just so small that nobody can measure it, basically is what they say. Oh, it has, and I agree, there's got to be something there, but nobody can really measure it with the equipment we have. Now, this is just energy, all energy. And an atomic bomb blast, this comes out first and the house burns up, and then this comes next and knocks the house over. And they are attached together as in an electron. This is an electron. We always thought there was no black particle. This is an electron. It has a black and a white. And the white has no mass. And a photon is back-to-back two of these. Now, what happens when you have an isotope? Right, don't forget, these are the only two. It's a white electron neutrino and a dark muon neutrino. That's it. That's the only two particles that make up everything that exists. Now, so where are the dark particles? They go to the center. That's what I never could understand. Well, I had a concept of dipoles, but I didn't realize that black could actually literally get away from the white. I just never realized that. Because a bar magnet, you can't break them apart. You cannot break a bar. You cut it, you got 2 bar magnets. You cut it again, you got 4, you got 8, you got 16, 32, 9, blah, blah, blah. So you could never get the black. But once you get down below the atomic range, then you can break them apart. And there's no question, there's absolutely zero question that that's true. So the black ones go to the center. That's why we've never seen them. Because anytime we look at something, all we can do is see the stuff that bounces back at us. This is like a cut across. Now, the more particles we have in the center, the bigger the isotope is. Once you hit stability, you got just enough particles surrounding that black. So there's just enough black, because the black makes the weight. So we know if the weight's going up higher and higher and higher, it has to be black particles, no question. The white has no mass. So if we have more and more and more mass, we have more and more and more black particles. That has to be. But that will attract more and more white, which you have no mass, but they have a lot more energy. So the bigger the ball in the center gets, the more energy you have here. That's why when you get up to plutonium and all that stuff, they got so many particles. They got a ton of white ones around them, which is the energy. Those are the things that kill you, or well, they'll burn you. These, if they come flying at you, will knock you over and kill you, like with gamma rays and X-rays and nuclear radiation. That's what you're getting there. When you get slammed with something hard, that's these. When you just get burnt, that's these. And I will show you that right now in the atomic bomb blast, because that's the best way to present this. But this is what a proton is made out of. And a nuclear bomb is nothing more than the black particles forced to the center, coated with just gobs of white, and then they coat that with extreme amounts of high energy bombs, and then they implode it in. And when they crush all those particles in so hard, they take off. And when they go, it's just a brilliant flash of these. No weight. There's no weight to those. So it's just a flash. I will prove it. And then comes the black ones that follow it, because they're pushed in and they're bouncing out with the rest of everything. And then after the explosion, everything will have to come back to fill in a literal void in space. A nuclear bomb makes a literal void. Everything, it comes in and then it goes out and then there's nothing there. And it has to come back. Can I prove that? Yes, I can. Okay, my friends, I'm going to leave it at this for today, but we're going to be going into rock identification. How do you identify rocks? Well, they give them names. I'm going to show you what they are in real life. And I can explain all of these most unbelievable rock formations on Earth. And this is a 30-minute long video. And then we're going to go into the identifying rocks. And I'll just be going through clips of what they're... And I'm sure they're going to do some talking about it, but I will too. But I will be showing you things like this and things like this that they don't pay attention to, I don't think, as much as I do. I've been doing this for a long time. I understand what I'm looking at, and I think you will too when I point it out. That's all. You just got to point it out and then let people make their own decision. But to make it not be able to be seen is a tragedy to humanity. And that's what's happened. It's considered false information, but they have no explanations for any of this. Why can't I have an explanation? If it's false, well, it's just a guess. These are only theories. I can't prove specifically what I'm saying, but I think I can show a pretty good case to support it. And if that's the case, well, that's the case.